Hello friends, welcome to this new module, that is module 2, and the part 2.1 from optics 1 is interference of light. So first of all, we will get to know a few terms. Those are wavefront, types of wavefront, and what is interference. Then we will be knowing what is coherence, the property of coherence, and coherent sources. So at any point, the continuous locus of all points having the same phase of vibration is called a wavefront. So let me write that down for you all. So here is the definition I have written for you all. Please note it down carefully. What is wavefront? At any moment, the continuous locus of all points having same phase of vibrations is called wavefront. So, according to the wave theory of light, a source of light spreads its disturbances in all directions. That is, if this is considered as a source of light, then if there is no barrier at one side, it will be spreading its disturbances in all possible directions. Like this. In all possible directions. So, in vacuum or in a homogeneous medium, the points those are situated at equal distances from the source of light will vibrate in the same phase. That is, if this is the source of light and these all are the possible directions of vibrations or disturbances spread from the source of light, then if I measure a radius of r from the source, a distance r, and I draw a circle here, then in the locus of the circle, or you can say in the circumference of the circle, the particles present there will have same phase of vibrations. That is known as wavefront of a particle. So, depending upon the shape of the source of light, wavefronts are of three types. We can classify them as three types. Number one is the spherical wavefront. Spherical wavefront. But number two is cylindrical wavefront. And number three is plane wavefront. We will be studying about plane wavefront in details in the next part, that is diffraction. So let me draw all the wavefront for you all. So as you can see, I have already drawn the three diagrams. This is number one, that is spherical wavefronts. That is, the example I have set up here is of spherical wavefront. In the distance, let us consider the distance as r. So if in the distance of r we consider and see the behavior of particles of light, then we will see a spherical wavefront. We will get a spherical wavefront. This one is number two, known as the cylindrical wavefront. As you can see from the shape, this is the mid-axis, and this is the mostly studied plane wavefront. So I think we have got the definition of the three kinds of wavefronts. Now we will move on to a important principle, that is Huygens Principle. So first, let me write down the definition for you all. So friends, here is Huygens Principle for you all. It states that each point on a primary wavefront acts as a secondary source, that is known as wavelets of disturbances, and spread in all possible directions. So let me show it by a small schematic diagram. If this is the source of light, that is the primary source, I am writing as PS, and it spreads light in these directions, or you can say it spreads disturbances in these directions. And if this is the primary wavefront, that is, these particles vibrate with same phase of vibrations that I have already written here, same phase of vibrations. So according to Huygens principle, it will act as the secondary source of light. That is, it will act, if we name this as S1, then after having the same phase of vibration, all of these sources will act as S1. That is, again, they will spread vibration in all possible directions, like this. Like this. So, if this particle again spread direction in all possible directions, then we'll get another wavefront. Similarly, again these particles will spread in another directions and we will get another wavefront. Like this, the disturbance is propagated. Like this, the light is propagated through the medium. So, we can also define a new term here, that is wave train. So, what is wave train? I am defining it. A wave train implies the continuous transfer of energy in the medium from the source of light energy. So, we can define it by the equation of a simple harmonic motion. That is, we can write y equal to a sine of 2 pi multiplied by small t by capital T minus x by lambda. So this is, as you all know, the equation of simple harmonic motion. So a simple harmonic wave train is represented by the equation of the displacement y at a point x from the source at time t, as I have defined here. In this equation, a is the amplitude and capital T is the time period, and lambda, as you all know, is the wavelength of the wave. So now, after defining all these terms, a new term is introduced, that is coherent source. So let me write down for you what are coherent source. So friends, here is the definition of coherent sources. As you all can see, note it down, two sources of light emitting waves of the same frequency. This is worth noting down, of the same frequency and nearly same amplitude but with a constant phase difference are called coherent sources. So if these are two sources, S1 and S2, with all these properties, maintaining all these properties that are same frequency, nearly same amplitude, but with a constant phase difference, then these two sources will be called as coherent sources. But in practice, it is not at all possible to have two independent coherent sources, as the phase difference of the two of the independent sources does not remain constant. If the phase difference changes rapidly in an irregular way, the resulting waves are not coherent and the corresponding sources are called not coherent sources. So we cannot practically obtain two different sources with constant phase difference and with the same frequency. So what we do to get coherent sources, we usually use a single source and divide it into two parts by the division of wavefronts or by the division of amplitude. So we can follow two methods to get two wavefronts, that is division of wavefront or division of amplitude. There are two methods. From examination point of view, only the definition and the purpose or the experiments in which these methods are used are important. So let me write down those for you. So the first one is division of wavefront. What is division of wavefront method? In case of division of wavefront, light from a single source is divided into two beams by the use of apertures or optical components which separate neighboring parts of the wavefront, and the separated beams are subsequently brought together. So this is the definition, how it works, but we need to know where it is used. So the experiments or the observations in which these are used are, one is Young's experiment or Young's double slit experiment that we are going to study in details. Then another one is Frenzel's biprism experiment, and also in Lloyd's single mirror. Lloyd's single mirror experiment. So these are the experiments where this method, that is division of wavefront, is used. In division of amplitude, a single beam is divided by means of partial reflection in a thin film or semi-transparent mirror, and the separated beams are superimposed subsequently. So here it is divided into two wavefronts by means of apertures, and here it is divided into two wavefronts by means of partial reflection in a thin film. So an important observation or an important experiment including division of amplitude method is Newton's ring experiment or Michelson's interferometer. Michelson's interferometer. So these, friends, are the examples where these methods are being used. We are going to study in a bit details Young's experiment and Newton's ring. So let us proceed further and know some more definitions. So now let us understand the different types of coherence. As we can see, there are two types of coherence. One is temporal coherence and another one is spatial coherence. So let me write down the definitions for you all. So friends, here I have written the definitions for temporal and spatial coherence. Let us understand this. When phase difference of any 2 points lying along the direction of propagation of wave does not change in between fixed interval of time, then the beam of light is called temporal coherence. Similarly, in spatial coherence, when the phase difference between any 2 points on the two waves lying on the plane perpendicular to the direction of wave propagation, so here is the difference, you can see it is perpendicular here in spatial coherence, does not change with time, then it is the case of spatial coherence. For example, the phase difference between any 2 points lying on the same wavefront is 0 at all times. The wave is then said to exhibit perfect spatial coherence. So these were some important definitions for you to know from an examination point of view. Now we will straight away go to interference of light, the definitions, and Young's experiment. So friends, this is the definition for the process of interference. Let me read it out for you. The phenomena in which alternate bright and dark fringes are produced as a result of two monochromatic light waves having same wavelength but a constant phase difference proceeding in the same direction. So you see the phenomena somewhat looks like this. If two waves, or you can say two sine waves, for example, if it is like this and it is the wave 1 and the second wave comes like this, is in phase, this is the second wave, so you see that trough to trough and crest to crest are matching in both the waves. So where two troughs meet, a bright region is observed. I am drawing the result here. Where two trough meets, a bright region is observed, and where two crest meet, a dark region is observed. So it somewhat look like this. If we point out the regions as A, this region, and this as B, this as C, this line is C, and region of this area is D, then E. So we can say we will be observing an area like this. I think you are getting this. So this is the area A, this will be the area B, again here will be area C, and here will be area D, and again there will be area E. So you can see that where troughs are meeting, we are getting a positive value, or we are getting the addition of the positive value. So we are getting the bright region, that is, you can say this region is bright region, and where the crests are meeting at B and at D, we are getting the dark region. So this is this one and this one and this one and this one, singles of them are known as fringes. So that is the phenomena of interference.